Hello there. Welcome to Science Verse. Before sleep, your quiet space for gentle science stories and peaceful nighttime curiosity. Here, we slow down the world for a moment and let the universe unfold softly around us. Now, settle in, breathe deeply, and let's begin tonight's journey into the universe of science. Picture this moment. Right now, as you listen to these words, you are moving, not just breathing, not just the gentle rise and fall of your chest, but truly moving through space at an almost unimaginable speed. Beneath your feet, the Earth spins. It rotates on its axis at roughly 1,000 miles per hour at the equator. You don't feel it. The air moves with you. The trees, the buildings, the oceans, everything participates in this ancient dance that began 4.5 billion years ago. But what if it stopped? What if, in a single moment, the Earth's rotation came to a complete and sudden halt? What would happen to you, to the atmosphere, to the vast oceans, to every living thing on this spinning blue marble we call home? Tonight, we're going to explore this question together. We'll journey through the science, the chaos, and the strange new world that would emerge if our planet's eternal spin simply ended. This is a story written in the language of physics and planetary science, but told with wonder. So settle in, close your eyes if you wish, and let your imagination drift into this impossible scenario. If you enjoy drifting into wonder, relaxing your mind, and ending your day with calm exploration, make sure to subscribe and join our growing nighttime community. Now, settle in, breathe deeply, and let's begin tonight's journey into the universe of science. Chapter 1: Understanding Earth's Rotation. Before we can understand what would happen if Earth stopped spinning, we need to appreciate what that spin truly means. The Earth rotates from west to east, which is why the sun appears to rise in the east each morning and set in the west each evening. This rotation takes approximately 23 hours, 56 minutes, and 4 seconds to complete one full turn. We round this to 24 hours for convenience, creating the familiar rhythm of our days. At the equator, where Earth's circumference is greatest at about 25,000 miles, the surface moves at roughly 1,040 miles per hour. That's faster than the speed of sound. As you move toward the poles, this speed decreases. At 45 degrees latitude, roughly the location of cities like Minneapolis or Milan, the rotational speed drops to about 730 miles per hour. At the poles themselves, you would simply rotate in place, spinning slowly like a figure skater at the center of their pirouette. But here's what's remarkable. You've never felt this motion. Not once in your entire life have you sensed the Earth spinning beneath you. This is because everything around you moves at the same speed. The air, the ground, the water in the oceans, even the clouds high above, all share this velocity. You are like a passenger on the smoothest train imaginable, moving through the cosmos without a single vibration or bump to remind you of the journey. The Earth's rotation gives us more than just the cycle of day and night. It creates the Coriolis effect, which influences weather patterns and ocean currents. It causes storms to rotate, hurricanes to spiral, and trade winds to blow in predictable directions. This spin affects how water drains from your sink, though not as dramatically as popular myths suggest. The rotation even causes Earth to bulge slightly at the equator, making our planet not a perfect sphere but an oblate spheroid, slightly flattened at the poles and bulging at the middle by about 27 miles. This bulge exists because of centrifugal force. As Earth spins, material is pushed outward at the equator. The oceans pile up there, creating a band of extra water around the planet's middle. Mountains at the equator are technically farther from Earth's center than mountains near the poles. Mount Chimborazo in Ecuador, though not the tallest mountain above sea level, is actually the point on Earth's surface farthest from the planet's core because it sits almost directly on the equator. The rotation also generates Earth's magnetic field through a process called the geodynamo. Deep within our planet, the liquid iron outer core flows and churns. Earth's rotation influences these flows, creating electric currents that generate a magnetic field extending far into space. This invisible shield protects us from the solar wind, the constant stream of charged particles flowing from the sunday. Without this protection, Earth's atmosphere would gradually be stripped away, much like what happened to Mars billions of years ago. So when we ask what would happen if Earth stopped spinning, we're not just talking about losing the day-night cycle. We're contemplating the collapse of interconnected systems that have defined our planet for eons. We're imagining the disruption of forces so fundamental that they shape the very form of the ground beneath our feet. Now, let's imagine the impossible becomes real. Let's imagine that in one sudden, catastrophic moment, the Earth's rotation ceases completely. What happens next? Chapter 2. The first seconds, catastrophic inertia. The Earth stops, not gradually, not slowly winding down over years or centuries, but instantly. In one frozen moment, the planet's rotation ceases completely. The ground comes to a halt, but you don't. Remember, at the equator, you've been moving at 1,040 miles per hour. The air around you, the trees, the buildings, the cars on the street, everything has been traveling at this speed. When the Earth stops, all of that momentum remains. You would be thrown eastward at over 1,000 miles per hour, like a passenger in a car that struck an invisible wall spanning the entire planet. The devastation would be beyond comprehension. Every person, animal, and loose object near the equator would be hurled eastward at supersonic speeds. Buildings not anchored to bedrock would topple and tumble. Trees would be ripped from the earth, their root systems no match for the violent forces. Cities would be scoured clean, reduced to debris fields in milliseconds. The human body, fragile and soft, would not survive the impact of colliding with the landscape at such velocities. But the destruction wouldn't be uniform across the globe. At the poles, where rotational speed is nearly zero, people might feel only a slight jolt, a momentary disorientation. They would be among the few to survive the initial moment, confused but alive. As you move from the poles toward the equator, the violence would increase proportionally. At mid-latitudes, the speed might be 700 miles per hour, still catastrophic. But perhaps, just perhaps, some structures built into mountainsides or deep valleys might offer protection to those lucky or unlucky enough to survive. Now consider the atmosphere. The air around Earth has mass. Roughly 5 quintillion tons of it wraps around our planet. When Earth stops, this enormous ocean of gas continues moving eastward at its original rotational speed. Near the equator, winds exceeding 1,000 miles per hour would scour the surface. These would make the most powerful hurricanes in recorded history look like gentle breezes. Category 5 hurricanes have wind speeds around 180 miles per hour. What we're describing is more than 5 times that velocity. These hypersonic winds would last for hours, gradually slowing due to friction with the now stationary surface. Mountains would act as barriers, creating turbulence that would eventually dissipate the momentum. But in those first hours, the atmosphere would be a weapon, sandblasting anything still standing, igniting fires through friction alone, creating sonic booms that would echo continuously across the landscape. The oceans present an even more terrifying scenario. Earth's oceans contain about 326 million trillion gallons of water. All of this water has been rotating with the planet. When the solid Earth stops, the oceans continue moving. Imagine tsunami waves, but not isolated events caused by earthquakes or underwater landslides. Instead, picture the entire ocean surging eastward as one continuous, planet-spanning wall of water. Coastal regions facing east would be completely submerged. The wave wouldn't be tall in the traditional sense, not like the towering walls of water in disaster films. Instead, it would be a sustained rise in sea level, a relentless flood moving at hundreds of miles per hour, carrying everything before it. Cities on the eastern coasts of continents would vanish beneath the surge. The water would penetrate miles inland, reshaping coastlines and drowning valleys. The western coasts would experience something equally strange. As the ocean rushed eastward, it would drain away from western shores, exposing the continental shelf. The seafloor would suddenly become dry land, at least temporarily, revealing underwater canyons, shipwrecks, and abyssal plains that have been hidden beneath the waves since the oceans formed. But we're not done with the immediate effects. Remember that Earth is not a rigid sphere. The planet itself has some elasticity, some give. The sudden stop would send seismic shock waves through the entire planet. Earthquakes of unprecedented magnitude would ripple through the crust. Every fault line would slip simultaneously. Volcanoes, their magma chambers compressed by the shock waves, would erupt. The ring of fire around the Pacific would explode into activity. Yellowstone, Vesuvius, the Icelandic volcanic systems, all would awaken at once. The ground would literally ripple like a drumhead struck by an invisible hand. These seismic waves would propagate through the planet's interior, reflecting off the boundary between the mantle and core, returning to the surface to cause secondary quakes. Cities built on sedimentary basins or near tectonic boundaries would experience liquefaction, where solid ground temporarily behaves like a liquid. Skyscrapers that somehow survived the initial inertial impact would sway and collapse as their foundations failed. In the first minutes after Earth stopped spinning, the planet would be unrecognizable. Fire and water, wind and stone, all would conspire to erase nearly every trace of human civilization. The few survivors would be scattered, isolated, trapped in whatever geological features provided shelter from the chaos. They would emerge into a world transformed, a world where the familiar rules no longer applied. But the catastrophe of the first moments would only be the beginning. The longer-term effects, the ways in which the stopped rotation would reshape Earth's fundamental systems, would be even more profound. What happens next? Before we move to the next chapter, kindly click on the subscribe button and turn on notification if you're yet to do so, and tell me where you're watching from. Take a moment here. Breathe slowly, in through your nose, out through your mouth. The scenario we're exploring is, of course, impossible. The laws of physics that govern our universe make such a sudden stop inconceivable. No force exists that could halt Earth's rotation so abruptly. But in imagining the impossible, we gain appreciation for the delicate balance of our world, for the countless factors that must align perfectly to create a planet where life can flourish. As you rest, consider the ground beneath you, still and solid, yet hurtling through space at tremendous speed. Consider the air in your lungs, moving with you, protecting you. Consider the vast machinery of Earth, the rotation, the magnetic field, the water cycle, all working in harmony to create the conditions for this moment, for your existence. When you're ready, we'll continue our journey into this strange, stopped world. We'll explore what happens in the hours and days that follow, how the survivors might cope, and what new equilibrium Earth might eventually find. Chapter 3: The Hours After Atmospheric Chaos. Let's imagine that somehow, impossibly, you survived. Perhaps you were in a deep bunker or a cave system, or somehow sheltered in a valley, positioned just right. The initial violence has passed. The hypersonic winds are beginning to slow. The seismic activity is gradually subsiding to more typical earthquake magnitudes. You emerge to witness the new world. The first thing you would notice is the sky. Without Earth's rotation, the familiar patterns of clouds and weather systems would immediately begin to change. The Coriolis effect, which causes moving air and water to curve to the right in the northern hemisphere and to the left in the southern hemisphere, would no longer exist. Storms would no longer rotate. Hurricanes would dissipate within hours, their spiral structure collapsing. The global wind patterns that have shaped climate for millions of years would break down. The trade winds, which blow from east to west near the equator, exist because of Earth's rotation. The westerlies at mid-latitudes, the polar easterlies, all of these predictable currents would cease. In their place, a new pattern would gradually emerge, one driven purely by temperature differences between the equator and the poles, and between the day side and night side of the planet. Yes, day side and night side. Because with Earth's rotation stopped, one hemisphere would face the sun continuously, while the other would be plunged into eternal darkness. But we're getting ahead of ourselves. Let's stay in these first hours, before the day-night divide becomes extreme. The atmosphere, still carrying the momentum of Earth's former rotation, would take days or even weeks to fully synchronize with the stopped surface. During this transition period, the weather would be utterly chaotic. Winds would blow from unpredictable directions, changing hour by hour as the atmosphere gradually shed its angular momentum. Temperature gradients would form in strange patterns, creating localized storms and pressure systems unlike anything in Earth's meteorological history. The jet streams, Those narrow bands of fast-moving air high in the atmosphere that influence weather patterns across entire continents would meander and break apart. Commercial aviation, had it somehow survived the initial catastrophe, would be impossible. The reliable air currents that planes used to conserve fuel and maintain schedules would be gone, replaced by turbulent, unpredictable flows. Meanwhile, the oceans would still be in turmoil. The initial tsunami-like surge would have redistributed water across the planet, but the oceans wouldn't settle immediately. Large-scale currents, like the Gulf Stream and the Antarctic Circumpolar Current, which are driven by both wind and Earth's rotation, would persist for a time due to inertia. But without the Coriolis force to maintain them, these currents would gradually slow and dissipate. The redistribution of ocean water would be dramatic. Remember Earth's equatorial bulge? That bulge exists because centrifugal force pushes water toward the equator. With rotation stopped, this force vanishes. Over the course of weeks and months, water would begin to flow away from the equator toward the poles. The equatorial oceans would become shallower. Islands and coastal areas near the equator would find themselves with expanded land area as the water receded. Conversely, the polar regions would see sea levels rise dramatically. Some estimates suggest that without Earth's rotation, sea levels at the poles could rise by as much as 8 kilometers, or about 5 miles. The Arctic Ocean would deepen significantly. Antarctica, already covered by ice, would be submerged even more completely. The redistribution would create 2 new oceans, one around each pole, and expose land near the equator. This redistribution wouldn't happen instantly. It would be a gradual process, taking months or even years to reach a new equilibrium. But eventually, Earth would transform from a water world with scattered continents to a planet with a massive ring of land around its equator and 2 vast polar oceans. The geography we know would be unrecognizable. In these early hours and days, any survivors would face immediate challenges. Fresh water sources would be contaminated or destroyed by the flooding and seismic activity. The normal water cycle of evaporation, condensation, and precipitation would be disrupted. Agriculture would be impossible, as fields would be destroyed and the seasonal patterns plants depend on would no longer exist. Food stores would be buried, burned, or scattered across the landscape. Communication would be severed. Cell towers, power lines, satellites in orbit that somehow survived the initial disruption, all would be useless. The survivors would be isolated, small pockets of humanity separated by vast expanses of devastated terrain. They would have no way of knowing if anyone else had lived through the catastrophe. And hanging over everything would be the sun. For those on the day side, it would have frozen in the sky, fixed at whatever position it held at the moment of the stop. If the stop occurred at noon, the sun would remain at its zenith, beating down relentlessly. If it occurred at dawn, the sun would hang just above the horizon, casting long shadows that never moved. For those on the night side, darkness would have fallen, complete and total, broken only by the stars and the moon, if it happened to be in the sky at that moment. But the moon's position would also seem strange. The moon orbits Earth, taking about 27 days to complete one circuit. With Earth not rotating, the Moon would appear to move across the sky in a slow arc over the course of 2 weeks, then disappear below the horizon for another 2 weeks. The tides would still occur, driven by the Moon's gravity, but they would be slow, predictable, nothing like the complex tidal patterns created by the interaction of rotation, the Moon's orbit, and the shape of ocean basins. As the hours stretched into days, the temperature divide between the sun-facing hemisphere and the dark hemisphere would begin to grow. We'll explore that in detail shortly. But first, let's consider what would happen to one of Earth's most important systems, one that operates far above the surface, yet affects every living thing below. What happens next? Chapter 4: The Magnetosphere and Solar Wind. Far above the chaos at Earth's surface, something else would be changing. Something invisible, yet vital to all life on Earth. The magnetosphere, Earth's protective magnetic bubble, would begin to falter. Deep within Earth, some 1,800 miles below the surface, lies the outer core. This region is composed primarily of liquid iron and nickel, heated to temperatures exceeding 9,000 degrees Fahrenheit, hotter than the surface of the sunday. This liquid metal is in constant motion, churning and flowing in complex patterns, driven by heat from the inner core and influenced by Earth's rotation. As this conductive fluid moves, it generates electric currents. These currents, in turn, create a magnetic field through a process known as the geodynamo. Earth's rotation is crucial to this process. It influences the patterns of flow in the outer core through something called the Coriolis force, the same force that affects the atmosphere and oceans. The rotation creates columnar flows aligned with Earth's rotational axis, and these organized flows are essential for maintaining a strong, stable magnetic field. If Earth stopped rotating, the geodynamo wouldn't cease immediately. The outer core has enormous inertia. It would continue churning for some time, perhaps months or even years, gradually slowing due to friction and the lack of rotational forcing. But the organized structure of the flows would begin to break down almost immediately. The convection patterns would become more chaotic, less efficient at generating a coherent magnetic field. Over weeks and months, Earth's magnetic field would weaken. It might not disappear entirely, as heat-driven convection alone can sustain some level of magnetic field, but it would become much weaker and less stable. The field might fluctuate wildly, with the magnetic poles wandering across the surface or even reversing multiple times as the system sought a new equilibrium. Now, why does this matter? Why should we care about an invisible magnetic field weakening? The magnetosphere is our shield. It extends tens of thousands of miles into space, deflecting the solar wind, a constant stream of charged particles flowing from the sun at speeds of about 1 million miles per hour. These particles, mostly electrons and protons, carry enormous energy. When they interact with Earth's magnetic field, they're diverted around the planet, flowing past us like water around a stone in a stream. Without this protection, the solar wind would strike Earth's atmosphere directly. The particles would collide with molecules of oxygen and nitrogen in the upper atmosphere, stripping electrons from them in a process called ionization. Over time, this bombardment would erode the atmosphere, carrying it away into space bit by bit, molecule by molecule. This process wouldn't happen overnight. Earth's atmosphere is massive, about 5 quadrillion tons of gas. Even the intense bombardment of the solar wind would take millions of years to remove a significant fraction of it. But the effects would be noticeable much sooner. The immediate consequence would be increased radiation at the surface. The magnetic field and atmosphere together shield us from harmful radiation, cosmic rays, and high-energy particles that can damage living cells and DNA. With a weakened magnetosphere, more of this radiation would penetrate to the ground, especially in the polar regions where magnetic field lines converge and the protective effect is naturally weaker. Any survivors of the initial catastrophe would face elevated cancer risks and increased rates of genetic mutations. Electronics would be more vulnerable to damage from energetic particles. Satellites, had they somehow remained functional, would have their lifespans dramatically shortened. The beautiful auroras, the northern and southern lights, would become more frequent and more intense, visible at lower latitudes as charged particles struck the atmosphere directly. But there's another effect, more subtle but equally important. The interaction between the solar wind and Earth's upper atmosphere would increase heating in those high-altitude layers. The thermosphere, the atmospheric layer from about 50 to 400 miles above the surface, would become significantly warmer. Hot gases expand, and this expansion would cause the outer edges of Earth's atmosphere to swell outward. This might seem like a minor detail, but it would have cascading effects. The denser upper atmosphere would increase drag on satellites, causing them to lose altitude more quickly. The boundary between space and atmosphere would become blurred, and the chemistry of the upper atmosphere would change, altering the way sunlight interacts with atmospheric gases, potentially affecting the ozone layer that shields the surface from harmful ultraviolet radiation. The loss or weakening of the magnetosphere would be a slow disaster, unfolding over years and decades rather than hours or days. It wouldn't be the immediate cause of extinction, but it would make Earth's surface a more hostile place for life, adding one more challenge to an already catastrophic situation. But let's return to the surface, to the more immediate and dramatic changes that would transform Earth in the days and weeks following the stop. Let's talk about what happens when half the planet bakes under an unmoving sun, while the other half freezes in eternal darkness. What happens next? Chapter 5, the day side and the night side. Imagine standing at the terminator, the boundary between day and night. Before the Earth stopped, this boundary swept around the planet at roughly 1,000 miles per hour, creating the familiar cycle of sunrise and sunset. But now, it's frozen. On one side, the sun hangs in the sky, motionless. On the other, stars glitter in an unchanging darkness. Let's visit the day side first. If the Earth stopped with your location facing the sun, you would witness something no human has ever seen, a sun that never moves. Hours would pass, then days, then weeks, and still the sun would remain in exactly the same position. If it stopped at high noon, you would experience perpetual noontime. The sun directly overhead, shadows short and dark, the heat relentless. The temperature would begin to climb immediately. Without the relief of nighttime cooling, the ground would absorb solar radiation continuously. In the first day, temperatures might rise to 120 or 130 degrees Fahrenheit in many regions. By the second day, 140. By the end of the first week, surface temperatures in some areas could exceed 160 or even 170 degrees Fahrenheit. This is hot enough to denature proteins, to cook flesh. Any exposed water would evaporate rapidly. Lakes would steam away. Rivers would dry up. The moisture in the soil would be drawn upward by the heat, evaporating into the air. The day side would slowly transform into a desert, then into something more extreme, a landscape of baked earth and stone where nothing could survive. But the heating wouldn't be uniform. Remember, Earth's surface is tilted relative to its orbital plane around the Sun by about 23.5 degrees. Depending on what time of year the Earth stopped rotating, different parts of the planet would face the Sun more directly. If it stopped during Northern Hemisphere summer, the North Pole might actually face toward the Sun, experiencing constant daylight, while the South Pole would be in darkness. The sun's heat would drive powerful convection currents in the atmosphere above the day side. Hot air would rise, creating a massive, permanent low-pressure zone. This rising air would need to go somewhere. It would flow high in the atmosphere toward the night side, creating a simple but powerful atmospheric circulation pattern unlike anything in Earth's current climate. Now let's cross the Terminator and visit the night side. In the eternal darkness, the temperature would plummet. Without sunlight to provide heat, the ground would radiate its warmth into space through infrared radiation. In the first night, temperatures might drop to freezing. By the second night, well below 0 Fahrenheit. After a week, temperatures in some regions could reach -50 or -100 degrees Fahrenheit. Any water on the night side would freeze solid within days. Lakes would become ice. The moisture in the air would condense and freeze, falling as snow. This snow would accumulate, day after day, week after week, never melting. The night side would become a frozen wasteland, buried under layers of ice and snow that could eventually reach depths of hundreds of feet or more. But the cold air would be dense, heavy. It would sink, creating a massive high-pressure zone over the night side. This air would flow outward along the surface, moving toward the day side to replace the rising warm air. At the Terminator, where the cold night side air met the hot day side air, a permanent storm zone would form. This would be a band of violent weather encircling the entire planet. Imagine a hurricane, but one that never moves, never dissipates, stretching in a continuous ring around Earth. The temperature difference between the hot day side and the frozen night side would be so extreme that winds in this storm zone could reach hundreds of miles per hour. Lightning would flash constantly. Torrential rains would fall on the dayside edge of the terminator as moisture evaporated from the hot regions condensed in the cooler air of the storm zone. The terminator zone might be the only place where liquid water could exist on the surface, a narrow band where temperatures remained moderate enough for water to stay in its liquid state. This band would migrate slightly with the seasons as Earth continued its orbit around the Sun, but it would always remain roughly in the same location relative to the Sun's position. Any survivors would be forced to migrate to this zone. The day side would be too hot, the night side too cold. Only in the twilight band, in the perpetual dawn or dusk, could human life persist. It would be a harsh existence, battered by constant storms, but it might be survivable. Over months and years, the temperature extremes would grow even more pronounced. The day side might reach temperatures exceeding 200 degrees Fahrenheit in some regions, hot enough to melt some types of plastics. The night side could plunge to temperatures rivaling Antarctica at its coldest, below minus 150 degrees Fahrenheit. But temperature wouldn't be the only change. The redistribution of water vapor would dramatically alter Earth's appearance from space. The day side, losing water to evaporation, would become brown and red, a parched sphere of desert. The night side would become white, covered in snow and ice. The terminator, fed by moisture from both sides, might support a thin band of clouds that never moved, a permanent ring of weather wrapped around the planet like a belt. In this new configuration, Earth would no longer be the blue marble, the beautiful, vibrant world we know. It would become a planet of extremes, hostile to life, divided into zones of fire and ice, with only a narrow strip of habitability between them. And yet, life is tenacious. Evolution has produced organisms that thrive in boiling hot springs and others that survive frozen in ice for centuries. Could life adapt to this stopped Earth? Could ecosystems develop in the twilight zone? Could humanity, scattered and struggling, find a way to persist? These are questions we'll explore. But first, let's take another break. To rest your mind, consider the light and darkness, the heat and cold, the way our world's gentle spin protects us from such extremes. What happens next? If you're yet to subscribe, kindly do, so as not to miss new cosmic stories. Close your eyes for a moment. Picture yourself standing under a night sky. The stars wheel overhead, familiar constellations rising in the east, setting in the west, the same celestial dance humans have watched since our species first looked upward. This motion, this apparent movement of the heavens, is really our own rotation, reflected in the sky. In a world without spin, the stars would be fixed. Constellations would never rise or set. The North Star would no longer mark the celestial North Pole, guiding travelers and sailors. Instead, the sun would trace a slow path across the sky over the course of a year, moving through the zodiac constellations as Earth orbited. But each day, if we can even call them days anymore, would be identical to the last. Breathe slowly, in and out. Feel the stillness. In this imagined world, stillness would be the defining feature. No sunrise, no sunset, just the eternal now, frozen in temperature and light. When you're ready, we'll continue. We'll explore what happens to the long-term evolution of this strange planet, how the oceans settle, how life might adapt, and whether Earth could ever spin again. Rest now. The journey continues. Chapter 6: The Long-Term Evolution, Oceans and Continents. Weeks have passed since the Earth stopped spinning. The initial chaos has subsided. The atmosphere has mostly synchronized with the stopped surface, though powerful winds still blow from the night side toward the day side and back again in a perpetual circulation. The seismic activity has reduced to occasional aftershocks. The redistribution of ocean water is well underway. Let's zoom out, both in space and time, and watch what happens over the months and years that follow. The oceans, no longer held at the equator by centrifugal force, continue their slow migration toward the poles. This process reveals geography hidden for billions of years. The mid-Atlantic ridge, the underwater mountain range where tectonic plates spread apart, emerges from the waves near the equator. Islands in the Pacific and Indian Oceans gain land area as the surrounding sea level drops. The continental shelves, the shallow underwater extensions of the continents, become exposed. These regions, once rich in marine life, now become new land. Ancient shipwrecks rest on what is now dry ground. Coral reefs, adapted to warm, sunlit waters, die as they're exposed to air and sunlight, their skeletons bleaching white, creating bizarre fossilized landscapes. Meanwhile, at the poles, the water accumulates. The Arctic Ocean deepens. Islands like Svalbard and Franz Josef Land are submerged. The northern coasts of Russia, Canada, and Alaska disappear beneath rising waters. In the south, the seas around Antarctica rise, covering all but the highest peaks of the Transantarctic Mountains. Over the course of a year or two, Earth develops two massive polar oceans, separated by a ring of land around the equator. This ring would include parts of all the continents. The Americas would be connected by the exposed seafloor of the Caribbean and the Gulf of Mexico. Africa and South America might be linked by new land in the South Atlantic. Australia and Asia could be joined by the exposed shallow seas between them. This new geography would dramatically affect the flow of ocean currents. In our rotating Earth, currents are driven by wind, temperature differences, salinity differences, and the Coriolis effect. On a stopped Earth, the Coriolis effect is gone. Currents would be driven purely by temperature and salinity. The day side, hot and dry, would experience intense evaporation. This would leave the remaining ocean water saltier, denser. This dense, salty water would sink and flow along the ocean floor toward the night side, where it would cool further and continue to sink. The night side, fed by moisture from the day side that falls as snow and ice, would eventually melt at the edges of the polar oceans, creating fresh water that would flow back toward the day side along the surface. This would create a simple but powerful thermohaline circulation, a conveyor belt of water moving between the hot equatorial regions and the cold poles. But unlike Earth's current thermohaline circulation, which takes centuries to complete a full cycle, this new circulation might move more slowly, driven only by extreme temperature and salinity gradients. The exposed equatorial land ring would become the defining feature of Earth's new geography. Vast deserts would stretch across former ocean basins. Salt flats would glitter white under the unmoving sun. Deposited as ancient seawater evaporated, strange geological formations would emerge. Underwater volcanoes and seamounts now standing as isolated peaks in the desert landscape. But not all of this new land would be barren. Remember the Terminator Zone, the band of perpetual twilight. Where this zone crossed the exposed land, conditions might be suitable for life. Temperatures would be moderate. Moisture from the atmospheric circulation would fall as rain. Here, in this narrow strip winding around the planet, vegetation might eventually take hold. Plants need a day-night cycle to regulate their growth and metabolism through circadian rhythms, but they can adapt. Some plants already survive in extreme environments, like the Arctic summer, where the sun doesn't set for months. On a stopped Earth, evolution would favor plants that could photosynthesize continuously or that could enter dormancy periodically based on internal timers rather than external light cues. The Terminator ecosystem would be strange and narrow. Imagine a band of vegetation, perhaps a few hundred miles wide, encircling the planet. On the day side edge, hardy desert plants adapted to intense heat and constant sunlight. On the night side edge, cold adapted species similar to Arctic tundra vegetation. In the middle, where conditions were most moderate, perhaps something resembling temperate forests, though unlike any forest that exists today. This vegetation would support animal life, assuming any animals survived the initial catastrophe. Insects, small mammals, birds, all would need to adapt to the new conditions. Migration patterns would change completely. Instead of migrating north and south with the seasons, animals might migrate around the Terminator band, following the slight seasonal shift as Earth orbited the sun. The two polar oceans would develop their own ecosystems. The day-side ocean, fed by water from the Terminator Zone, would be warm at its edges, but cooler in the depths where cold water upwelled from the deep circulation. The night-side oceans would be frozen at the surface near the poles, but might have liquid water beneath the ice, insulated from the frigid air above. These dark, ice-covered oceans would resemble the conditions believed to exist beneath the ice shells of moons like Europa or Enceladus. Life could potentially survive there, perhaps near underwater volcanic vents where heat and chemicals provided energy, similar to the extremophile ecosystems discovered near Earth's current deep-sea hydrothermal vents. Now let's consider the geological evolution of the stopped Earth. Plate tectonics, the movement of Earth's crustal plates, is driven by heat from the planet's interior and is largely independent of Earth's rotation. The plates would continue to move, though perhaps differently than before. Convection currents in the mantle, the layer of hot, slowly flowing rock beneath the crust, would persist. Plates would still spread apart at mid-ocean ridges and collide at subduction zones. Volcanoes would still erupt, mountains would still rise, but the redistribution of mass on Earth's surface, the shift of ocean water to the poles, would alter the stress patterns in the crust. Regions that were previously under ocean water would rebound upward as the weight of the water was removed. This is similar to what happens in areas that were covered by ice sheets during the last ice age. Scandinavia, for example, is still rising by several millimeters per year as the crust rebounds from the weight of the glaciers that melted 10,000 years ago. The exposed equatorial regions would rise, potentially by hundreds of feet over thousands of years. Conversely, the polar regions, now bearing the weight of the redistributed ocean water, would sink. This would create a feedback effect. As the equatorial regions rose, water would continue to flow toward the poles, increasing the load there, causing more sinking, which would create more space for water, and so on. Volcanic activity might increase in the equatorial band as the reduction in overlying water pressure allowed magma to rise more easily. New volcanic islands could form in the shallow equatorial seas. Existing volcanoes might become more active. The Ring of Fire, the zone of volcanic and seismic activity around the Pacific, would continue to exist, though its pattern might shift as stress patterns in the crust changed. Over thousands of years, erosion would reshape the exposed equatorial land. Without vegetation to hold the soil, wind and the occasional rainfall at the terminator zone would carve deep canyons and valleys. Dust storms on the day side would rival those seen on Mars, lifting fine particles high into the atmosphere, where they would be carried toward the night side by the atmospheric circulation, eventually falling as colored snow on the ice. The night side ice sheets would grow thicker over time. Snow would accumulate year after year, century after century, compressing the lower layers into glacial ice. Eventually, these ice sheets could reach depths of several miles, similar to the ice sheets that currently cover Antarctica and Greenland. The weight of this ice would further depress the polar crust, creating deep basins. But ice is not static. Under its own weight, glacial ice flows like a very slow liquid. The polar ice sheets would spread outward from the poles toward the terminator zone. At their edges, they would calve icebergs into the polar oceans or melt, returning water to the hydrological cycle. This would create a dynamic equilibrium. Water evaporating from the day side would be carried by winds to the night side, where it would fall as snow and accumulate as ice. The ice would flow and melt at its edges, returning liquid water to the oceans, which would circulate back toward the day side to begin the cycle again. Earth would become a machine for moving water from day to night and back again, a perpetual engine driven by the sun's heat and the cold of space. Over tens of thousands of years, the landscape would stabilize into a new equilibrium. The continents would be reconfigured. The climate zones would be permanently fixed in place. Life, if it survived, would have adapted to the new conditions, creating ecosystems unlike anything that ever existed on rotating Earth. And through it all, the sun would hang motionless in the dayside sky, and the stars would remain fixed above the frozen night side, eternal and unchanging. But we haven't yet addressed one of the most profound questions. Could humanity survive this catastrophe? If so, what would their civilization look like? What happens next? Chapter 7: Human Survival and Civilization. Let's imagine that against all odds, some humans survived. Not many. Perhaps a few thousand scattered across the Terminator zone, sheltered by chance or preparation in underground facilities, caves, or structures that happened to be positioned to withstand the initial violence. These survivors would emerge into a world that bore no resemblance to the one they knew. The sky would be alien, the sun frozen in place, or absent entirely depending on their location. The temperature would be extreme. Communication networks would be gone. Most infrastructure would be destroyed. They would be alone. The first challenge would be immediate survival: food, water, and shelter. Any stored food that survived the catastrophe would be precious. Canned goods, dried foods, seeds. These would need to be rationed carefully. Hunting and foraging would be nearly impossible initially, as most animal life would have perished and plants would be buried or destroyed. Water would be the most critical resource. Survivors on the day side would need to collect water from the rare rainfall at the edges of the Terminator zone. Survivors on the night side would need to melt ice. Those lucky enough to be near the Terminator itself would have the best access to liquid water, though it would often come in the form of violent storms. Shelter would need to protect from both temperature extremes and the violent weather. Underground facilities would be ideal, insulated from the surface conditions. Caves, especially those near the Terminator, would become valuable territory. Any surviving buildings would need to be reinforced to withstand the constant high winds. But humans are remarkably adaptable. If the survivors could make it through the first weeks and months, they would begin to organize. Small groups would form, pooling resources and knowledge. Engineers, doctors, farmers, anyone with useful skills would become invaluable. The survivors would need to migrate to the Terminator zone if they weren't there already. This band of twilight would become the thin strip where human civilization could persist. Here, temperatures would be survivable, with appropriate clothing and shelter. Water would be available, and with time and effort, agriculture might be possible. But what kind of agriculture? Plants need light for photosynthesis, but they also need darkness to regulate their growth. The constant dim light of the Terminator zone would require adaptation. Perhaps survivors would create artificial day-night cycles using shelters with controllable lighting. Or perhaps they would cultivate plants that could handle constant low-light conditions, similar to shade-loving species or plants adapted to the brief growing seasons of polar regions. Greenhouses would be essential. These could be positioned to maximize the available twilight, perhaps with mirrors or lenses to concentrate the limited sunlight. Geothermal energy, tapping the heat from Earth's interior, could provide warmth and power. Wind energy would be abundant, as the constant circulation between the day and night sides would create reliable, strong winds along the terminator. Over generations, a new form of human civilization might emerge. Settlements would be strung along the terminator zone like beads on a string, connected by trade routes that wound around the planet. These routes would need to navigate the violent storm zone, the boundary between the habitable twilight and the extreme conditions on either side. Travel would be dangerous. Expeditions to the day side to harvest salt, minerals, or other resources would require protective equipment and strict time limits to avoid heat stroke. Expeditions to the night side to mine ice or explore the frozen landscape would require insulation and heating. Both would require careful planning and courage. The culture of this new humanity would be shaped by their environment. The sun and stars, once symbols of time and change, would become fixed landmarks. Navigation would be different, no longer based on the rising and setting of celestial bodies, but on their fixed positions. The terminator itself might become a sacred boundary, the line between the habitable world and the deadly extremes beyond. Timekeeping would change. Without the day-night cycle, what would define a day? Perhaps survivors would use mechanical clocks or hourglasses to maintain a rhythm of activity and rest. Or perhaps they would develop a new system based on shifts, with different groups working and sleeping on different schedules to make full use of the dim but constant light. Stories and myths would emerge, tales of the time before, when the world spun and the sun rose and set. These stories would take on the quality of legends, of a golden age lost. Children born in the stopped world would find it hard to imagine a sun that moved, hard to comprehend the concept of seasons or the march of days. Technology would evolve in new directions. Without access to fossil fuels, which would be difficult to extract and transport, civilization would be forced to rely on renewable energy. Wind, geothermal, perhaps even solar panels, positioned on the day side with long cables carrying electricity to settlements in the terminator zone. Radio communication might be restored, allowing isolated communities to connect across vast distances. But the population would likely remain small, perhaps never exceeding a few 100,000. The habitable zone would be limited. Resources would be scarce. Every individual would be precious. Every life essential to the survival of the species. Perhaps this scarcity would create a more egalitarian society where cooperation was necessary for survival. Or perhaps it would lead to conflict, to competition over the best locations and resources. Over centuries, humans might adapt biologically. Evolution would favor traits that allowed survival in the twilight zone, perhaps enhanced night vision or greater tolerance for temperature extremes. Skin pigmentation might change, becoming more uniform as there would be no selective pressure from varying sunlight intensity. The circadian rhythms tied to the day-night cycle might fade, replaced by internal timing mechanisms independent of external cues. And perhaps, just perhaps, knowledge would be preserved. Books, data stored on durable media, oral traditions passed down through generations. The history of rotating Earth, the science that explained the catastrophe, the technology that once allowed humans to thrive across the globe. This knowledge would be treasured, a link to the past and a hope for understanding the present. Could this civilization ever grow beyond mere survival? Could they develop science and art, philosophy and exploration? It's possible. Humans have created beauty and knowledge in the harshest environments. From the Arctic Circle to the Sahara Desert, from isolated islands to high mountain peaks, our species has always reached beyond simple survival to create meaning and culture. The stopped Earth would be a harsh teacher, but perhaps humanity would learn its lessons. Perhaps in the twilight zone, a new chapter of human history would be written, different from anything that came before, but no less worthy. But what about other forms of life? We've talked about humans, about plants and animals in general terms, but let's dive deeper. How would evolution respond to this catastrophe? What strange and wonderful species might emerge? What happens next? Take a moment to feel your breath, in and out, the most basic rhythm of life. Your body knows this rhythm without thinking, a cycle as old as the first organisms that crawled from ancient seas to breathe the air. Life is rhythm, the beating of your heart, the cycle of hunger and satiation, the need for sleep and waking. These rhythms would continue even in a world without the day-night cycle, proof that life carries its own time within itself. In the stopped world, life would struggle. Many species would vanish, but some would endure. Evolution never stops. Every generation, every mutation, every adaptation is life's way of exploring possibilities, of finding solutions to the challenge of survival. Rest here for a moment. Consider the resilience of life, its stubborn refusal to yield. From the deepest ocean trenches to the highest mountain peaks, from boiling hot springs to frozen glaciers, life finds a way. In our imagined stopped Earth, life would find a way too. Let's explore how. Chapter 8: Evolution in the Twilight Zone. Evolution is not a quick process. It requires generations, time for beneficial mutations to spread through populations. But when conditions change dramatically, evolution can accelerate. The stopped Earth would be such a time, a massive environmental shift that would create intense, selective pressure. In the Terminator zone, where conditions were most favorable for life, ecosystems would gradually rebuild from whatever species managed to survive. Let's imagine what forms life might take over thousands or millions of years. Plants would face unique challenges. Photosynthesis requires light, but most plants have evolved to handle alternating periods of light and darkness. The constant dim twilight of the terminator zone would favor species that could photosynthesize efficiently in low light conditions. Mosses and ferns, which thrive in shaded environments, might dominate initially, but over time, flowering plants might evolve adaptations, perhaps leaves that could rotate to track the sun's fixed position, maximizing light capture throughout the plant's growth cycle, or perhaps plants with internal rhythms that allowed them to rest and grow in cycles independent of external light. The lack of seasons would eliminate annual plants that complete their life cycle in one growing season. Instead, perennials would dominate, long-lived species that could grow continuously or in self-regulated cycles. Trees might evolve to be shorter and sturdier, adapted to the constant high winds. Their roots would need to be strong, anchored deep in the soil. Flowering and pollination would need to be triggered by internal timing rather than seasonal cues. Some plants might develop clocks, measuring time in circadian rhythms, flowering every 24 hours, despite the constant light level. Others might use temperature variations or moisture levels as cues, responding to the slight changes caused by weather patterns rather than day and night. Animals would undergo equally dramatic evolution. Insects, with their rapid generation times, would adapt quickly. Flying insects would need to cope with the constant winds. Perhaps they would evolve to fly low to the ground, or to be active only during lulls in the wind. Pollinators would need to synchronize with the flowering cycles of plants, developing internal clocks or responding to chemical signals. Larger animals would face the challenge of regulating their activity without the day-night cycle. Most animals have circadian rhythms controlled by internal biological clocks, but these clocks normally synchronize with external light cues. In the constant twilight, animals might develop longer or shorter activity cycles, or their circadian rhythms might become more variable, leading to populations where individuals were active at different times. This could actually be an advantage, reducing competition for resources. Imagine a species where some individuals hunt or forage while others sleep, with the roles shifting based on individual clocks rather than a shared day-night cycle. It would create a more continuous use of the ecosystem, with activity spread across all hours rather than concentrated in daylight. Predators and prey would evolve new strategies. Without darkness to hide in, prey animals couldn't rely on being active at night. Instead, camouflage would become even more important. Perhaps species would evolve to blend with the permanent twilight, gray and brown coloring that matched the dim landscape. Echolocation might become more common. Bats and dolphins use echolocation to navigate and hunt, and this ability doesn't depend on light. In the dim twilight or complete darkness of the night side, species that could navigate by sound would have an advantage. Perhaps land animals would evolve this ability, creating a world where clicks and chirps filled the air as creatures felt their way through the environment. The edges of the terminator zone, where it met the dayside desert or the nightside ice, would be zones of extreme adaptation. Desert edge species would need to tolerate high heat and conserve water, perhaps becoming nocturnal in behavior even though there was no night, simply retreating to burrows during the hottest periods and emerging to the marginally cooler terminator zone to feed. On the ice edge, species might evolve heavy insulation, thick fur or feathers, and perhaps even the ability to enter torpor, a hibernation-like state, to conserve energy during periods when food was scarce. These species might migrate along the terminator as it shifted slightly with Earth's orbit, following the narrow band of moderate temperatures. In the polar oceans, beneath the ice of the night side, life would face perhaps the greatest challenges. Sunlight wouldn't penetrate the ice, so photosynthesis would be impossible except at the very edges where ice met open water. Life would need to rely on chemosynthesis, deriving energy from chemical reactions rather than sunlight. Near underwater volcanic vents, where heat and minerals flowed from Earth's interior, microbial communities would thrive. These microbes would form the base of a food web, consumed by larger organisms adapted to the dark, cold, high-pressure environment. Strange eyeless fish might evolve, navigating bilateral lines that sensed water movement. Giant isopods, amphipods, and other crustaceans might thrive, scavenging whatever organic matter drifted down from above. Over millions of years, the ecosystems of the stopped Earth would become increasingly alien to our eyes. Species would diversify to fill every available niche in the narrow, habitable zone. Competition would drive specialization. Symbiotic relationships would develop, species working together to survive in the harsh conditions. Perhaps fungi would play an even larger role than they do on current Earth. Fungi don't photosynthesize. They break down organic matter and absorb nutrients. In the dim twilight, where plants struggled, fungi might decompose plant material and become a major food source for animals, creating food webs based more on decomposition than on active photosynthesis. And what about intelligent life? Would humans remain the only intelligent species, or would other animals evolve greater cognitive abilities? In harsh environments, intelligence can be advantageous, allowing animals to solve problems, use tools, and cooperate in complex ways. Perhaps dolphins or octopuses in the polar oceans would evolve greater intelligence, developing complex communication and social structures. Perhaps ravens or crows, already among the most intelligent birds, would evolve further, creating rudimentary cultures and tool use. Or perhaps humans would remain alone, the sole keepers of knowledge and technology on a planet that had become inhospitable to complex civilization. One thing is certain, life would not surrender easily. The history of Earth is a history of mass extinctions and recoveries. 5 times in the past 500 million years, catastrophic events have wiped out the majority of species, and 5 times, life has bounced back, diversifying into new forms, exploring new possibilities. The stopped Earth would be another such event, perhaps the greatest extinction of all. But in its aftermath, in the narrow twilight zone and the dark depths of the polar oceans, life would persist. Evolution would continue its endless experiment, creating new species, new ecosystems, new solutions to the challenge of existence. And perhaps, millions of years in the future, a biologist from the Terminator Zone would study fossils and wonder about the ancient world, the time before the stop, when the planet spun and life thrived across its entire surface. They would piece together the story of the catastrophe and the long recovery that followed. They would marvel at the resilience of life. But we're not done with our exploration yet. There's one more major question to address, one that reaches into the very depths of our planet and the mechanics of the cosmos. Could Earth ever start spinning again? What happens next? Chapter 9. Could Earth spin again? This is perhaps the most intriguing question of all. We've explored the catastrophe of the stop and the long-term adaptations that would follow. But is the stopped state permanent? Or could some force, some event, set Earth spinning once more? Let's consider the possibilities. First, let's remember what causes Earth to spin in the first place. The rotation is a remnant from the formation of the solar system. About 4.5 billion years ago, a cloud of gas and dust began to collapse under its own gravity. As it collapsed, it started to spin, pulled by the angular momentum of the particles within it. This is similar to how figure skaters spin faster when they pull their arms in. As the cloud flattened into a disk, the material in the center formed the sun, while the material in the disk clumped together to form planets. Each planet inherited angular momentum from the rotating disk, giving them their initial spins. Earth has been rotating ever since, gradually slowing due to tidal forces from the moon, but still carrying that primordial momentum. For Earth to stop spinning, as we've imagined, would require removing all of that angular momentum. For Earth to start spinning again would require adding angular momentum back, and that's not easy. Angular momentum is conserved in a closed system, meaning it can't be created or destroyed, only transferred between objects. So what could transfer angular momentum to a stopped Earth? The most obvious candidate is a massive impact. If a large asteroid or even a small planet struck Earth at an angle, it could impart enough angular momentum to set the planet spinning again. This is actually how the moon is thought to have formed. About 4.5 billion years ago, a Mars-sized object called Theia collided with the early Earth. The impact was so violent that it vaporized part of both objects, creating a disk of debris that eventually coalesced into the moon. The impact also contributed to Earth's rotation and may have knocked Earth's axis to its current tilt. For a stopped Earth, an impact that could restart rotation would need to be massive, delivering an enormous amount of energy and angular momentum. The object would need to be at least the size of a large asteroid, hundreds of miles across. and strike at an oblique angle rather than head-on. The consequences of such an impact would be catastrophic, of course. The energy released would be equivalent to millions or billions of nuclear weapons. The impact site would be vaporized. Seismic waves would circle the globe multiple times. Volcanism would increase dramatically. The atmosphere would be partially blown off into space. Life, if it had managed to survive and adapt to the stopped Earth, would face another extinction event. But if life could survive again, if any organisms managed to endure the impact winter and the subsequent chaos, they would eventually find themselves on a planet that once again rotated. The day-night cycle would return. The Coriolis effect would resume. The oceans would redistribute. Earth would slowly return to something resembling its pre-stop state, though the specifics of rotation rate and axial tilt would depend on the details of the impact. Are there any other mechanisms that could restart Earth's rotation? The answer is not really. Not any that are remotely plausible. The tidal force from the Moon, which currently causes Earth's rotation to slow very gradually, couldn't restart a stopped planet. The Moon's gravity pulls on Earth's oceans and crust, creating bulges that drag against Earth's rotation, converting rotational energy into heat. But this force only works to slow rotation, not to accelerate it. If Earth stopped spinning, the Moon would continue orbiting, but it wouldn't cause the planet to start rotating again. Solar wind, the stream of charged particles from the Sun, carries some angular momentum, but nowhere near enough to affect Earth's rotation. The same is true for magnetic interactions with the solar wind. These forces are far too weak to move an entire planet. Internal processes within Earth also couldn't restart rotation. The core might continue rotating independently of the mantle for a while, maintaining some angular momentum, but this internal rotation would gradually sync with the stopped surface through friction and magnetic coupling. There's no mechanism for the core to then transfer that angular momentum back to the surface to restart global rotation. So the answer is stark. Once stopped, Earth would remain stopped indefinitely unless a massive external force intervened. The stopped state would be the new normal, the permanent condition of the planet. This permanence is both sobering and fascinating. It means that any life that survived would truly be adapting to a new world, not waiting for a return to the old one. Evolution would proceed without the possibility of reverting to the previous environment. The Terminator ecosystems, human civilization in the twilight zone, the frozen polar oceans, all would be features of Earth for the remainder of the planet's existence. Unless, of course, another catastrophic event occurred. The solar system is not a static place. Asteroids wander on chaotic orbits. Gravitational interactions between planets occasionally fling comets into the inner solar system. The probability of a large impact is low on human timescales, but over millions or billions of years, it becomes increasingly likely. So perhaps, in the deep future, long after any observers had ceased to exist or had evolved into forms unrecognizable, Earth would be struck again. The impact would be violent, apocalyptic, but it might also be transformative, setting the planet spinning once more, creating a new cycle of day and night, restarting the climate systems and ocean currents, giving the planet a second chance at the dynamic, rotating existence it once had. And then, slowly, over millions of years, life would adapt again to the new conditions. New species would evolve. New ecosystems would form. The history of the stopped Earth would be preserved only in the fossil record, a strange interlude between two ages of rotation. It's a reminder of the vast timescales over which planetary evolution occurs. To us, with our lifespans measured in decades, 1,000,000 years seems incomprehensibly long. But to Earth, 4.5 billion years old, a few million years is the blink of an eye. The planet has time. Life has time. They experiment. They adapt. They endure. But let's pull back from these deep futures and consider one more aspect of our thought experiment. Throughout this journey, we've focused on Earth itself, but Earth doesn't exist in isolation. It orbits the sun. It has a moon. It exists within the broader context of the solar system. How would the stopped rotation affect these relationships? What happens next? Chapter 10. Earth's place in the solar system. Imagine floating in space, far enough from Earth to see the whole planet at once. From this vantage point, the stopped Earth would present a strange sight. One hemisphere, bright and hot, covered in brown deserts and glittering salt flats. The other hemisphere, white and cold, buried under ice sheets that gleamed in the starlight. Between them, a band of gray and blue, the terminator zone where life clung to existence. But this view would change, not because of Earth's rotation, which would remain stopped, but because of Earth's orbit around the sun. Earth would continue its annual journey around the sun, taking 365 days to complete one orbit. This orbit is what creates our seasons on the current, rotating Earth. As Earth orbits, different parts of the planet tilt toward or away from the sun, changing the intensity and duration of sunlight each region receives. On a stopped Earth, the orbit would create a different kind of seasonal effect. Let's say Earth stopped with the equator facing directly toward the sun at solar noon. Initially, the sun would be directly overhead at the equator on the day side. But as Earth orbited, the sun's apparent position would begin to shift. After 3 months, when Earth had traveled a quarter of the way around its orbit, the sun would no longer be directly overhead at the equator. Instead, it would appear lower in the sky, shifted either north or south, depending on which point in Earth's orbit the stop occurred. After 6 months, at the opposite side of the orbit, the sun would have shifted to its maximum angle. This means the terminator zone, the band of twilight, would migrate slightly over the course of a year. Settlements in the terminator would experience a subtle annual cycle. For part of the year, they might be in deeper twilight, with the sun lower and the temperature cooler. For another part, they might be in brighter twilight, warmer and more hospitable. This migration might only amount to a few hundred miles of movement over the course of the year, but it would be significant for any life trying to survive in the narrow habitable zone. Plants and animals would need to migrate with the shifting conditions or develop adaptations to handle the temperature variation. Human settlements might become nomadic, moving gradually around the terminator to stay in the most favorable conditions. Alternatively, humans might build permanent settlements and simply endure the seasonal variation, using stored food and energy during the less favorable portions of the year. This would create an annual rhythm, a substitute for the day-night cycle that was lost. Now let's consider the Moon. Earth's companion would continue its orbit, taking about 27 days to circle the planet. From the day side, the Moon would appear to move slowly across the sky over the course of 2 weeks, then disappear below the horizon for another 2 weeks. The Moon would still go through its phases, waxing and waning, though the timing would seem strange without the familiar day-night cycle to contextualize it. The Moon's tidal force would continue to affect Earth's oceans. High and low tides would still occur, though they would be much simpler than current tides. On rotating Earth, tides are complicated by the interaction between the Moon's pull, the Sun's pull, and the planet's rotation. On stopped Earth, the tidal bulges would be more straightforward, following the Moon's position more directly. The terminator zone might experience the most dramatic tidal effects. As the Moon's gravity pulled the polar oceans, water would flow toward the terminator, temporarily raising sea levels there before flowing back as the Moon moved on. These tidal flows could be substantial, creating powerful currents that survivors might learn to harness for energy or predict for navigation. The Moon's orbit would also create one of the few time markers available on the stopped Earth. The lunar month, the 27-day cycle from new moon to new moon, could become the primary unit of time measurement. Instead of counting days, survivors might count moons. A year would be about 13 lunar months. Children might grow up thinking of time in terms of moon cycles, rather than the daily cycles we take for granted. From the night side, the Moon would be a rare gift of light in the eternal darkness. When the Moon was in the sky, the frozen landscape would be faintly illuminated, casting long shadows across the ice. The full moon would be particularly significant, perhaps celebrated by any survivors brave enough to live near the night side edge of the terminator. It would be a reminder that light existed even in the darkest places. Now, let's zoom out even further and consider Earth's relationship with the Sun itself. The Sun is not static. It's gradually getting brighter as it ages, and in about 1 billion years, it will be hot enough that Earth's oceans will begin to evaporate regardless of any other factors. Eventually, in about 5 billion years, the Sun will expand into a red giant, swallowing Mercury and Venus, and possibly Earth as well. A stopped Earth would face this same fate, but the journey there might be different. Without rotation, Earth's magnetic field would weaken, as we discussed earlier. Over millions of years, this weakened field would allow more solar wind to strip away the upper atmosphere. The process would be slow, but inexorable. Simultaneously, the intense heating on the day side would cause water vapor and other gases to escape more readily into space. The hottest parts of the day side might eventually lose most of their atmosphere, becoming nearly airless like the moon. The night side would retain its atmosphere better, as the cold temperatures would cause gases to condense and freeze rather than escape. This would create an atmospheric imbalance. Air would continuously flow from the night side, where it accumulated, to the day side, where it escaped. The atmospheric pressure might gradually decrease over millions of years. The Terminator ecosystems would need to adapt to thinner air, perhaps by moving to lower elevations where the pressure was higher. But these are changes that would unfold over geological timescales, millions of years. Any civilization or species surviving on stopped Earth would have time to adapt, to migrate, to evolve. The stopped Earth would not be a static snapshot, but a continuously changing world, just like rotating Earth, but changing in different ways and responding to different forces. There's something profound about contemplating these vast stretches of time. It reminds us that Earth's current state, with its comfortable rotation and familiar climate, is just one moment in a long history. The planet has been snowball Earth, completely frozen. It's been hot enough to have no ice caps. It's been struck by asteroids, shaken by supervolcanoes, suffocated by toxic atmospheres. And through it all, life has persisted, adapted, evolved. The stopped Earth, as catastrophic as it would just be another chapter in this long story. A strange chapter, certainly, an uncomfortable one for any species that lived through the transition, but not the end of the story. As we near the end of our journey through this impossible scenario, let's take one more break to rest and reflect. We've traveled from the initial catastrophe through millions of years of adaptation and evolution. We've imagined human survival and alien ecosystems. We've contemplated the planet's place in the cosmos. When we return, we'll explore some final questions and scenarios. What if Earth stopped gradually instead of suddenly? What if it stopped at different times of year? And what deeper truths does this thought experiment reveal about our world and our place in it? Rest now, breathe. The final chapters await. Chapter 11. Alternative Scenarios. What if? Throughout this journey, we've imagined a sudden, catastrophic stop. But what if the scenario were different? Let's explore some alternative possibilities and see how they might change the outcome. Scenario 1. A gradual stop. Imagine instead that Earth's rotation began to slow gradually, taking years or decades to come to a complete halt. Perhaps some unknown force exerted a constant drag on the planet, or perhaps tidal forces from an approaching massive object began to break Earth's spin. In this scenario, the immediate catastrophic effects would be avoided. There would be no sudden inertial violence, no hypersonic winds or planet-spanning tsunamis. Instead, humanity would have time to observe and understand what was happening. The first signs would be subtle. Days would become slightly longer. not enough to notice at first, but precise atomic clocks would detect the change. Scientists would be puzzled, then alarmed as they realized the trend was continuing. Days that were once 24 hours would stretch to 24 hours and 1 minute, then 24 hours and 10 minutes, then an hour longer. Seasons would become confused. Climate patterns would shift as the Coriolis effect weakened. Storms would lose their characteristic rotation. Ocean currents would slow and meander. The jet streams would become erratic. As days grew longer, plants would struggle. Crops would fail, adapted as they were to specific day-night cycles. Some regions might initially benefit from longer growing seasons, but as days stretched to 30, 40, 50 hours, the extended heat during the long day and cold during the long night would become problematic. Humanity would have time to prepare. Deep underground shelters could be built in the anticipated terminator zone. Food stores could be accumulated. Energy systems could be developed that didn't rely on the day-night cycle. Perhaps most importantly, knowledge could be preserved. Libraries, digital archives, seed banks, all the accumulated wisdom of civilization could be protected. When the planet finally stopped, weeks or months after the slowdown began, survivors would be ready. The transition would still be traumatic, the loss of life substantial, but it wouldn't be the near total extinction of the sudden stop scenario. Humanity would have a better chance of maintaining some level of technological civilization. Scenario 2. Stopping during different seasons. The effects of the stop would vary depending on when during the year it occurred. Earth's axis is tilted at about 23.5 degrees relative to its orbital plane. This tilt creates our seasons. During Northern Hemisphere summer, the North Pole tilts toward the sun. During Northern Hemisphere winter, it tilts away. If Earth stopped during Northern Hemisphere summer, the North Pole and Arctic regions would be on the day side, experiencing constant sunlight. The South Pole would be on the night side, in constant darkness. The terminator zone would run roughly along lines of latitude, north and south of the equator, creating a habitable band that favored the Northern Hemisphere. Conversely, if the stop occurred during Northern Hemisphere winter, the Southern Hemisphere would be favored. The South Pole would receive constant sunlight, while the North Pole froze in darkness. The terminator zone would shift south of the equator. The most balanced scenario would be a stop during the equinoxes, when neither pole tilts toward the sun. In this case, the terminator zone would run roughly along the meridians, lines of longitude, creating a band of habitability that circled the globe from north to south rather than east to west. Each scenario would create different geographical advantages. Certain continents might be entirely on the day side or night side. Island nations might disappear beneath the redistributed oceans or gain new territory from exposed seafloor. The specific details would dramatically affect which populations had the best chance of survival. Scenario 3. Tidally locked to the moon instead of stopped completely. Here's an interesting variation. What if instead of stopping completely relative to the sun, Earth became tidally locked to the moon? This is the situation the moon is currently in relative to Earth. The same side always faces us, which is why we never see the dark side of the moon from Earth's surface. If Earth became tidally locked to the moon, it would rotate once every 27 days, the same period as the moon's orbit. From Earth's surface, the moon would appear to hang motionless in the sky, never rising or setting. The sun, however, would still appear to move, taking 27 days to cross the sky from horizon to horizon. This would create days and nights, but they would be 27 times longer than our current day-night cycle. Nearly 2 weeks of daylight, followed by nearly 2 weeks of darkness. The temperature swings would be extreme, though not as severe as a complete stop. Plants and animals would need to adapt to these long cycles, perhaps by migrating around the globe to stay in the twilight zones at dawn and dusk. This scenario is actually not entirely implausible. Over very long timescales, billions of years, Earth and the Moon will likely become mutually tidally locked, with each always showing the same face to the other. The process is already underway. Tidal forces are gradually slowing Earth's rotation and pushing the Moon into a slightly higher orbit. Of course, this won't happen for billions of years, long after the Sun has made Earth uninhabitable anyway. But it's a reminder that Earth's rotation is not eternal, not unchanging. It's gradually winding down, just extremely slowly. Scenario 4. Reverse rotation. What if Earth didn't stop, but instead somehow reversed its rotation? What if it began spinning west to east instead of east to west, so that the sun rose in the west and set in the east? If this happened suddenly, it would be even more catastrophic than a simple stop. The momentum change would be twice as large. The planet would need to lose its current angular momentum and then gain it again in the opposite direction. The inertial effects would be doubled. Nothing would survive. But if it happened gradually, the effects would be fascinating. The Coriolis effect would reverse, causing storms to rotate in opposite directions. Trade winds would blow the other way. Ocean currents would reverse. The Gulf Stream, which currently carries warm water from the tropics to the North Atlantic, keeping Europe warmer than it would otherwise be, would flow in the opposite direction. Climate zones would shift. Regions that were wet might become dry and vice versa. Deserts might bloom while rainforests dried out. Ecosystems would need to adapt to completely new patterns of temperature and precipitation. Humans would find it disorienting. The sun rising in the west would feel fundamentally wrong, a violation of the natural order. Navigation would need to be relearned. East and west might switch meanings, or new terms might be developed to avoid confusion. This scenario is even more impossible than a simple stop, as there's no plausible mechanism for it to occur. But it's a useful thought experiment for understanding how deeply Earth's rotation is embedded in every aspect of our world. These alternative scenarios remind us that the specific details matter: the timing, the speed, the nature of the change, all of these would dramatically affect the outcome. But in every scenario, the fundamental truth remains: Earth's rotation is not just a background detail. It's central to everything we experience, everything we are. Now, as we approach the end of our journey, let's pull all of these threads together. Let's reflect on what this impossible thought experiment reveals about our world, about science, and about ourselves. What happens next? Chapter 12: Reflections and Deeper Truths. We've journeyed together through a catastrophe that could never happen. We've watched continents reshape, oceans migrate, climates transform. We've imagined the struggle for survival, the adaptation of life, the persistence of hope in a world turned hostile. But why? Why spend so much time exploring an impossible scenario? Because impossibilities can illuminate truths that possibilities obscure. By imagining Earth without its rotation, we've come to understand what that rotation truly means. It's not just a number in a textbook, not just the reason for day and night. Earth's rotation is woven into the fabric of our world in countless ways we never consciously appreciate. It shapes our weather, creating the trade winds that carried explorers across oceans and the jet streams that now carry aircraft. It sculpts our oceans, driving currents that distribute heat around the globe and support marine ecosystems. It protects us, generating the magnetic field that shields us from radiation. It even influences our biology, embedding circadian rhythms deep in our cells that regulate everything from sleep to hormone production. When we imagine all of this being taken away, we gain perspective. We see that our normal, everyday experience rests on a foundation of physical laws and planetary conditions that must align just so. Earth's rotation, its distance from the sun, the presence of the moon, the composition of the atmosphere, the existence of liquid water, all of these are not guarantees. They're gifts, accidents of cosmic history that created a world where life, and eventually consciousness, could emerge. This thought experiment also reveals something about resilience. Even in the most catastrophic scenario we could imagine, life would likely persist somewhere. In the Terminator zone, in the deep ocean, in underground caves, life would find a way. Evolution would continue. New forms would emerge. This resilience is not unique to our thought experiment. It's a feature of life on Earth. Through ice ages and impact events, through volcanic eruptions and atmospheric changes, life has endured for nearly 4 billion years. Each catastrophe has been followed by recovery, diversification, and new complexity. The same is true of human resilience. Throughout our relatively brief existence as a species, humans have faced ice ages, megadroughts, disease, pandemics, and countless other challenges. We've adapted, migrated, invented, persevered. The survivors in our stopped Earth scenario would do the same. drawing on the same creativity and determination that has always characterized our species. There's also a deeper lesson about interconnection. In exploring the stopped Earth, we've seen how every system connects to every other. The atmosphere depends on the rotation. The oceans depend on the atmosphere. Life depends on the oceans. The magnetic field depends on the rotation. Everything links to everything else in a web of mutual dependence. This is true of our actual Earth as well. Climate, geology, biology, chemistry all interweave. Change one element and ripples spread through the entire system. This understanding is crucial as we face real challenges like climate change. Small shifts in atmospheric composition or ocean temperature can cascade through the Earth system in complex, sometimes unpredictable ways. Our thought experiment also highlights something beautiful: the mediocrity of our situation in the best possible sense. Earth is not at an extreme. It's not the fastest rotating planet, that's Jupiter, or the slowest, that's Venus, which rotates so slowly that its day is longer than its year. It's not the hottest or the coldest. It's in the middle, in what we call the Goldilocks zone, where conditions are just right. This mediocrity is actually extraordinary. Of the thousands of exoplanets we've discovered, none are quite like Earth. Many are too hot, orbiting too close to their stars. Many are too cold, frozen in the outer reaches of their solar systems. Some are gas giants without solid surfaces. Others are tidally locked, always showing one face to their star, creating day and night sides even more extreme than our stopped Earth scenario. Earth's gentle 24-hour spin is rare, special, even if we never notice it. The fact that you can watch a sunrise, experience the heat of midday, witness a sunset, and feel the cool of night, all in a single day, is a gift of rotation. It creates variety within predictability, change within stability. As we near the end of our journey, there's one more reflection to share. This entire exploration has been an exercise in imagination guided by science. We've used physics, geology, biology, and astronomy to project forward from an impossible premise. This is what science does at its best. It takes our curiosity, our what-if questions, and provides a framework for exploring them rigorously. Science doesn't just tell us what is. It helps us understand what could be, what must be, what cannot be. It reveals the rules of the game, the constraints and possibilities that shape our universe. And in doing so, it feeds our imagination, opening up vistas of wonder that are grounded in reality, yet reach toward the infinite. So, as you drift towards sleep, or simply toward the end of this audio journey, carry these reflections with you. Remember that the ground beneath your feet is spinning through space. Remember that the air in your lungs is part of a vast atmospheric dance driven by that spin. Remember that the sun will rise tomorrow not because it must, but because of a chain of physical processes billions of years in the making. Remember that you live on a rare and precious world, a blue marble spinning in the void, and that your existence depends on countless factors aligning in just the right way. And perhaps, most importantly, remember that understanding this makes it not less magical, but more so. We have one final chapter, a closing, a return to the beginning, a moment of peace before we part ways. What comes next? We've traveled far together, you and I, from the catastrophic moment of the stop through millions of years of adaptation and change. We've visited the fire of the day side and the ice of the night side. We've walked the Terminator zone where life clings to existence. We've imagined humanity's struggle and life's resilience. But now it's time to return to the real Earth, the spinning Earth, the Earth where tomorrow the sun will rise just as it has for billions of years. Right now, as you listen to these words, somewhere on Earth the sun is rising. Light is spreading across a landscape, waking birds and warming stone. People are stirring, beginning their days. In a few hours, that same sun will be directly overhead, marking noon in a different part of the world. Later, it will set, painting the sky in colors of amber and rose, before the night brings stars and quiet. This cycle will repeat tomorrow and the day after, and for billions of days to come, until the sun itself grows old and swells into a red giant, or until some event we cannot foresee changes the eternal dance. But that day is not today. Today, the earth spins, the sun rises and sets, the seasons turn, the tides ebb and flow. You are part of this dance, whether you feel it or not. Your body knows the rhythm. Your cells count the hours. Your blood flows in time with the ancient spin of the planet beneath you. Perhaps after this journey, you'll notice things you didn't notice before. The way the sun's angle changes as the day progresses, the direction of the wind, the spiral of water draining from a sink, the stars wheeling overhead at night. All of these are fingerprints of rotation, small evidences of the great spin. Perhaps you'll feel gratitude for the ordinary miracle of sunrise. Perhaps you'll marvel at the complexity of a simple summer day, at the interplay of light and heat, wind and water, life and stone. Or perhaps you'll simply sleep, resting in the knowledge that Earth's spin continues, that day will follow night, that the systems that support your life are stable and strong. The Earth turns 1,000 miles per hour at the equator, carrying you through space. You don't feel it, but it's real as your breath, as real as your heartbeat. And in spinning, Earth creates the conditions for your existence, for all existence. The rotation is not just a fact, it's a gift, a cosmic inheritance from the birth of the solar system, passed down through 4.5 billion years to this moment, to you, to now. Rest now. Let your mind drift. Let the images of the stopped earth fade like a dream. Return to this world, this good earth, spinning faithfully through the cosmos. You are safe. You are held. The ground beneath you is steady even as it moves. The sky above you wheels in its ancient pattern. Day follows night follows day in endless succession. This is home. This is Earth, spinning, living, extraordinary. Thank you for journeying with me through this impossible world. May your dreams be peaceful, may your sleep be deep, and may you wake to a sunrise, a gift of rotation, a reminder of the precious, fragile, beautiful world we share. Good night. Rest well. The earth spins on.